Hello students, we're going to go over B5 written section of the exam. I'm going to go over everything that's already in the OneNote, but I'm going to try to explain things in case people are unsure of some of the explanations. For number one, we have a 50 ohm resistor connected to a 3-volt battery. In the diagram, or in the circuit diagram shown, there is a voltmeter and an ammeter connected to the circuit. So the ammeter is connected in series with the battery and the resistor. The voltmeter is connected in parallel to the battery and the resistor for that matter. In the question, we are told that the current coming out of the battery is 59 milliamps. It's asking us to find the internal resistance of the cell. So for this question, it's basically about do you understand internal resistance? Internal resistance is a natural property of all batteries that are not exactly ideal. So like an ideal battery has no internal resistance, but in real life, all batteries have a little bit of internal resistance. A lot of the time, a question will state if there is internal resistance or if there is no internal resistance. Most of the time, if you're looking at a circuit, you can assume there's no internal resistance unless it is specifically stated, because that does affect pretty much everything in the circuit. It affects the total resistance of the circuit, it affects the current coming out of the circuit, it affects the voltage coming out of the battery. So it's very important to understand internal resistance. Okay, so for part A, we have an equation. It's basically E equals I times the quantity capital R plus lowercase r. We're given all this information. We're given 3 as the battery EMF. Now 3 is what is supposed to be the voltage of the battery, or the ideal voltage. So it says EMF. The current needs to be converted to milliamps, and we're given the resistance of the circuit. Now, there was only one resistor, so we just put 50 in here. If there was more resistors, we'd put the total resistance of the circuit. The internal resistance is 0.85 ohms, small amount. Usually this number is small in comparison to the rest of the circuit. In part B, we see that another resistor has been added, in parallel in this case. Explain the effect of this change on B.I, the reading of the ammeter, and B2, the reading of the voltmeter. The ammeter obviously measures the current coming out of the battery, and then the voltmeter obviously measures the voltage of the battery, or of the total resistance of the circuit. So one thing that's important to understand is if you add a battery in parallel, you're going to use this equation, 1 over RP. So RP stands for, should be R parallel. But sometimes we just say the total resistance, because both the resistors are, there's only 2 resistors in the circuit. So the total resistance is the R total. So 1 over R, we don't know, plus 1 over 50. We can solve for 1 over R and do some adding of fractions and take the inverse of those fractions, and we get R equals 25. Important to know that the overall resistance of a circuit goes down when a resistor is added in parallel. So you could continue to add resistors in parallel and the overall resistance will go down. So how does this affect the ammeter? Well, the reading in the ammeter will go up because the equivalent of the R equivalent of the circuit goes down. So this is interesting. Some students might think the opposite. They might think if you're adding more resistors, the resistance should go up and the current should go down because more resistance makes the current slower. But this is not the case, because basically when you add more resistors, it basically draws more current from the battery, the overall resistance of the circuit goes down, and that's seen here with our equation. So our equation basically tells us that. Maybe students don't know that right away from looking at the equation, but that's what the equation tells us. And so simply the circuit current goes down. Or sorry, the equivalent resistance goes down and the circuit current goes up. And this is all based on V equals IR. For part 2 here, we have to look at this equation here. So part 2 here, we look at this equation, E equals I times R. So I have annotated this equation here. And it says, since the current is going up, this part here, this IR part of the equation, increases and it takes away more from the voltage. The potential difference is what is measured in the voltmeter. Okay, so if I goes up, it takes away from the EMF, and then the PD actually goes down. So the voltage, or PD, goes down because the current goes up. This is basically what happens in real life. You can't really add resistors forever because at some point the current will go increase and just take away from the voltage that it is that is being supplied. So in an ideal battery, yeah, you could add it and the current would go up and up and up. But in real life, as the current goes up, it takes away from the voltage, and there's limits to that, to what would happen there. All right. This next part here, part C, is all about resistivity. This part doesn't seem too difficult. You're really just going to use the equation for resistivity, but you're going to solve for R. So here it is for R. And then we're going to set these two R equations equal to each other because it says solve for K. Now, K is just a random combination of numbers and variables that the question has created. So we're just going to say, well, what is K? So we're going to solve for K here because we put the R's equations equal to each other. K equals the resistivity. By the way, this P is resistivity over the area. We solve for that, and we get K is equal to 16 ohms per meter. So in a way, what does that mean? 16 ohms per meter means that basically every time you extend the wire a meter, you're extending it by the resistance by 16 ohms. So it's still a useful constant. Okay, moving on to question 2 here. So question 2 starts off with the diagram. It's a very simple split in current. Everyone should know that when current meets a junction, so like this black dot here is like a junction in a circuit. Sometimes people call it a node. Whenever current meets a node or a junction, it splits. It will always split if the circuit is completed, meaning there's no open sections in the circuit, so it's closed. But this is just showing us a junction. It doesn't really show us the rest of the circuit here. So it says the three wires are related. So I1 equals I2 plus I3. State the fundamental law. Well, this is a law of conservation of current, but the equation does have a name here. It's Kirchhoff's law. It just says that current is when current isn't lost, basically, when it splits. Okay. Part B, we've got another circuit here, and this is another circuit with internal resistance. This one actually shows us the internal resistance. The question from the circuit from question 1 didn't show the internal resistance, so we actually see it, and this is a typical way to show internal resistance. The dotted line is the battery, but it has internal resistance. The voltmeter is in parallel with the battery and the circuit and the resistor in this case. Here we have the original equation we used in question 1 again. We're going to plug in the resistance, capital R, the voltage. This is slightly different. No, I think this is the same equation. Let me see. Yeah, it's the same equation. So the one thing that we're not given is the potential difference. We're given the EMF. So obviously the EMF is the E. The current we have to solve for the current. Let me see here. The reading in the voltmeter. We're given the reading in the voltmeter. So since we're given the reading in the voltmeter, we're going to use the reading in the voltmeter to find the current. So over here, we found the current using V equals IR is 0.24. Okay? So you have to use the voltmeter reading to find the current, not the EMF value to find the current. And then we get an internal resistance of 1.25. So it's, again, a small number. So again, in this question, these questions are kind of similar. You just add another resistor in parallel. The voltage goes down. The voltage goes down because the current goes up. The current goes up because of this equation, PD equals E minus IR. And yeah, these two questions are very, very similar. Number 3, we're going to switch gears a little bit. Number 3 does not talk about internal. Oh, wait, it does. Internal resistance. Yeah. So number 4 maybe is the one that doesn't talk about internal resistance. Yeah, number 4 I think is okay. So all of these are internal resistance. All right. Number 3 has a graph. All right. So we see there's a graph in number 3. Oh, it says negligible internal resistance. Yes, negligible internal resistance for 3 and negligible internal resistance. All right, so I saw the word internal resistance, but it's negligible. Okay. All right. So I always mark up my circuits whenever I get information that I know. So I put the 6 volts in right away. We're given the graph. We're told that the R is ohmic. R is ohmic, meaning that as V increases, so does I, and vice versa. But basically, it increases in a linear fashion. If R is ohmic, then Q and P are not ohmic. So the graph shows us that Q and P are not ohmic because they have curved increases in current and as voltage increases. Basically, in real life, not all resistors are consistent at all voltages and currents because materials just don't always create a like a linear increase or relationship. It's close, like so there you do see an increase, but it's not exactly linear. Well, the question here is, what is the current in Q? Okay, so the current, so I put question mark Q here. In order to find the current in Q, and I'm sure there's a couple ways to do this, but I tried to find the voltage in Q. I know if I can find the voltage in P or R, then I can find the voltage in Q because I know all the voltage has to add up. Now, I've already shown all my work here, so you see that I found the voltage. But let me show you how the process in which I found the voltage. So in AI, I said if the current in IP is 4, then the voltage is 1.4. So how do I know that the current is 4? Well, that's told in the question. The current is 0.4. I go to the graph. So here you see in the graph, I have a dot at 0.4. I go to the graph and go over to the P line, P curve, go down to 1.4, and I see 1.4 voltage. Okay. If I know that P is 1.4 volts, so I put that in my diagram here, 1.4 volts. I know that VQ has to be 4.6. Now you might be asking, well, what about R? Well, R is also 1.4 volts. Now they're in parallel, so they must have the same voltage. And that's something you need to know about resistors in parallel. They have the same voltage. But even if I combine the resistance of P and R, you would see that resistors in series split up the voltage evenly. So you can treat P and R as one resistor when you're looking at the voltage. We sometimes do this where we draw equivalent circuits to just look at the voltage or certain parts of the characteristics of the circuit. All right. So, VQ should be equal to 4.6. So here I'm just writing out my answer. And the graph shows that if the voltage of Q is 4.6, then the current has to be 0.45. And that's my answer. So my answer is the current is 0.45 milliamps, right? Yes. No, it's 0.45 amps. I guess that would be like 450 milliamps. But this question is just in amps. Part 2, calculate the resistance of R. Okay, so we're going to use V equals IR here. So I've shown my work here. I know that the current in R is 0.05. Now, this was clearly stated in the previous question that if the current splits, it has to split evenly. So if the current going into, here, I'll just go back to the picture. If the current going into Q is 0.45, then the current going to P is 0.4, then the current going into R has to be the difference between those two things. So it's 0.05. All right, I think that's all you have to do for that one. Oh, no, we have to find the resistance, right? So we know the current, we know the voltage. We're going to use R equals V over I, and then we're going to find it's 28 ohms. And I drew a diagram here showing, oh yeah, if the current splits, it has to split equally. Okay. Next question. Calculate the power dissipated in the circuit. Okay, so this is P equals IV. We know that the voltage is 6 and the current is 0.45. This is the total current, and this is the total voltage, so 2.4 watts. This one is pretty easy, 1 point. If P is removed, state and explain without calculations the effect on the resistance of Q. So, okay, so in the previous questions, they asked, oh, if something was added, but now something is taken away. If P and R are in parallel, and in parallel of a resistor, if a resistor in parallel is removed, then the equivalent resistance goes up. So the equivalent resistance will go up, but the question is saying what happens to Q. And so if the resistance goes up, but everything else has to stay the same, then Q has to go down so that the total resistance stays the same. This is kind of an assumption on our part that they want us to talk about the resistance of Q being able to change. This is just something that you have to kind of figure out from the question, or because like resistors can change. Like there could be a variable resistor, and it doesn't say that, but yeah, I mean, there's no other way to explain what will happen to Q if the question is saying that the resistance can change. Okay, number four is somewhat similar to number 3. We've got a non-ohmic resistor. Now I did draw a blue line saying, oh, what if it was ohmic? It would just look linear. Number 4, we've got a variable resistor here, and the variable resistor shows 1.6 volts. I actually might have written that in. Let me see here. We're actually given 20 amps is what we're given. So I drew that into the circuit here. And then I said, okay, 20 amps is coming out of the battery, and it's going through the variable resistor, and it's going through X, right? But then it says component X and the cell are now placed in a potential circuit divider. Okay, so this is interesting. So here's the circuit divider. The circuit divider is called PQS. Interesting naming here. So outline why X is considered non-ohmic. Well, we know it's non-ohmic because you're looking at the graph. So Rx is non-ohmic because as V increases, I increases exponentially and not in a linear graph. So that part is not bad. That's kind of easy to answer. Just say, look at the graph. Part B1, determine the resistance of the variable resistor. Okay, so I'm assuming they're referring to the first diagram, that's second diagram. V equals IR. We know the I is 0.02, so we converted 20 milliamps to amps. We know the VR equals 1.6. The reason why we know okay, I have to go back to the graph here. So we know X has voltage of 2.4 because it has a current of 20 milliamps. So if you use the graph the exact same way you used the graph in question 3. Okay, so we know that it's 2.4, and the voltage of the variable resistance has to be 1.6. If the variable resistor is 1.6, and we know the current is 0.2, we just plug that into V equals IR, or R equals V over I, and we get 80. Okay. Part 2, calculate the power dissipated in the circuit. Okay, part 2, we're just going to do P equals IV. We know the voltage, and we know the current, so we get 0.08 watts. There's like a couple equations here, but this P equals IV is the one that most people use. All right, on to part C. The range of the current of the ammeter can measure as the slider S of the potential divider is moved from Q to P. Okay, so something we need to understand about the potential divider circuit is that it can change its resistance. It can change its resistance up and down. It's called a slider. I think all you really need to know is that it can change its resistance and output it's kind of like a different, so when it changes resistance, it can change the voltage in X, right? So these basically, you change resistance in one thing and it affects the voltage and current in another thing. Yeah, so I think that's really a state the range and current of the ammeter can measure the slider S. So the range of the current through the divider can be 0 or 60 based on the graph. Okay, so we look at the graph. And then describe by reference to your answer in C the advantage of the potential divider in B versus the potential divider in A, we'll say. I guess these aren't really labeled, so A is the first one, B is the second one. The second one is better because it has a higher range. The first one, there's really no option to not go through the variable resistor. Okay, so let me just try to explain this by looking at both of these pictures. In the first one, the 20 milliamps, or whatever the current is, has to go through both resistors. It has to go through the variable resistor and it has to go through X. Even if the variable resistor is 0, it still has to go through X. In the second one, if the PQS resistor is 0, it can just go through there and then not have to go through the other one. If the resistance is turned up, it basically makes the current very small. So you can change the current more in the second one. All right. What did I put as the answer? The current. so this should say current, must go through X for the first circuit, but not for the second circuit. Okay. Yeah, so these 4 questions, we're going to basically pick 2 of them. Definitely one with internal resistance and definitely one without for the exam.